Thank you all for coming. I'm excited to be here. What I present today is what we have been doing at Scholar Inbox, how we solved the cold start problem with active learning, and most of the stuff that I talk about originated from a master thesis 5 years ago, and now is being developed with a growing team at the University of Tübingen and the Max Planck Institute. So this is our team of students and full-time employees that have all joined this project, and our spiritual leader, Andreas Geiger, the professor. Yeah, and my role in this team is to be the tech lead. So during my PhD, I have done 5 years of experience in recommendation systems and in agentic LLM evaluations. And yeah, I've led this software team. So the outline for this talk today is, first I will tell you what this Scholar Inbox project is about, what problems we solve and how it works. So then I will give an introduction to two-tower recommender systems architectures. So this is the state of the art of how recommenders work nowadays. I will introduce the hierarchical document transformer, which is a work that has been done in our lab to increase the efficiency of our recommender, and introduce the cold start problem to you. Then I will talk about how we solved that with active learning. Yes, that's the outline. So these 3 parts are the technical parts, and the other parts are softer. You will see what I mean with that. So what is Scholar Inbox? It's a recommendation system for research papers. But what problem does that solve? Why do you need this at all? Well, if you think about how you learn about machine learning nowadays, there are basically not that many ways to get news, right? I would like you to think about, do you use Twitter maybe to learn about machine learning? Do you read the news? Or do you read research papers, right? Well, for the researchers and the PhDs, the solution is always the latter, and they always read research papers. But research has been expanding massively in the last few years. So according to this curve, you can see quite well when ChatGPT came out, which was beginning of 23, you can say. That's where it really took off, and we're in a kind of, you can say, almost exponential part of this curve, where we expect in the next 5 years to add 2 million research papers to the collective. And this is only in physics and mathematics and computer science alone. Of course, the other disciplines will also grow. So then if we narrow down a little bit more and imagine you're one researcher focused on, let's say, computer vision, then the number of papers per day that you will see is 700. So it's a very hard problem for you. You cannot even skim all the titles to decide what to read. So this is the problem that we're trying to solve with Scholar Inbox. And this is what it looks like to the user. On the left, you see we have a feed of our recommender that's providing a score for each paper, and only the best papers are shown to the user. This works really well, and 15,000 PhDs use it every month to guide their research here. So that's the user item relevance. Higher is better, of course. And we incite user feedback with this up-down vote. So keep that in mind. That will be basically the data foundation that I will use later to explain how we train our models. So these up and down votes, that's the essential bit. Yeah, and also we provide conference support. So there are some really large conferences in computer vision and robotics and so on. So CVPR has over 10,000 participants every year. And if you imagine such a huge conference where every scientist tries to present their poster, there are over 400 posters in each poster session. And we also apply our recommender to this problem, prioritizing the visit to this conference. You could imagine at MLCon, if there were a lot more talks and you needed to decide which one to go to, the recommender would help you there. Yeah, and this is also just a detail. We are paid by public funding, so this is paid by the European Research Council with 2 million and the Volkswagen Stiftung with 800,000 euros. So what I've been telling you is Scholar Inbox is like TikTok, but instead of cat videos, we have research papers. So how do the recommendations work? Now this is the part where we transition from the high-level overview into a more and more in-depth technical view, right? So we will arrive at the very bottom of the transformer later. So have a look here. This is a recommendation system. This is ours with a typical two-tower model architecture. So that's how recommenders work nowadays. Let's start at the bottom to explain this diagram. For each user, of course, we have a user ID that goes into the user tower, and on the item we have various item features. Our items are research papers themselves, so we have the title, the abstract, the body, the authors, the year, the figures that are part of the paper. All of this data goes in. And then we have various neural network architectures. So on the left, we have a rather shallow model that I will also explain later. And on the right, we have a dense transformer encoder model, which I will go into detail in a second. After that, both of these models provide an embedding. So there's a user embedding and an item embedding, where we form the dot product and get a similarity score out in the end. So this score is what you saw on the Scholar Inbox website. That's this relevance that you get out in the end. Yes, so then our loss function ensures that when we train here with papers that the user has liked, a high similarity comes out, and when we train with papers that have been disliked, a low similarity comes out. So we do that in a classification training setup. Okay, let's talk a little bit about this very dense item tower neural net that's on the right-hand side here. So I think you're familiar with transformer. Can I get a quick show of hands if anybody doesn't know transformer architecture? Maybe you don't want to out yourself, but it's like this paper came out in 2019. Attention is all you need. Very central for all the LLMs. Yeah. So this transformer is split in an encoder and a decoder. You can generally say that both parts of this transformer have been used in different ways. So the encoder, like BERT, Roberta, and GTE, is used for representation learning and presents vector embeddings for items, and that's also what we need. And the decoder on the right was used by GPT variants and Claude and DeepSeek and all the generative models that you know about today. They are decoder-only models. The difference really is just that for the decoder, the output is like generated autoregressively, so token by token, and each token that is generated also then becomes part of the input again, so that it, can generate token by token, whereas the encoder takes the entire input at once and produces an embedding for it. Okay, so I'm zooming in on the encoder a little bit because that's what we need. Here we have an input, right? Text. This will be like a sentence, tokenized, as you're probably aware, like with byte pair encoding, chunked into very small bits. With a vocabulary, and we add a positional embedding on top of that. Then comes a really important part, the multi-head self-attention block, some normalization, and feed-forward steps. Yes. So what I'm really interested in now is to look into this self-attention block and what's going on inside of here. So attention is the core of the transformer. This is the central part that we need to understand if we want to know how modern language models work, is this attention block. Here is an example. You can see the a sentence going in. So let's say the train left the station on time. And then doing this attention computation will do the dot product between the vector representation of each of these tokens. Essentially what that means is it does the semantic similarity between these tokens, right? So you can see that the train and the station token are pretty similar to each other, so they have 0.8. On this main diagonal, of course, everything is 1.0 because the self-similarity is 1. So then what's going to happen is that each, that the station token gets weighted by 0.8 and added to the train token, and the same for all of the other tokens, such that the most important tokens determine what is the semantic meaning of the target token for which these similarities are computed. Okay. Wow, I went into this great detail now because that's where we innovated. Here is another one of these attention computations. This is what I've told you basically, right? So this matrix that I showed was this thing in the bracket here, and then it's multiplied with the values as to do this weighted average. Well, not average, this weighted dot product. Yes. So here comes our innovation. We did a new kind of transformer encoder that that has a certain sparsity, which allows it to consume really large documents. And also, so that makes it train very fast and very efficiently. We call that the hierarchical document transformer by my good colleague Howie. Yes. So that's the overview slide. Doesn't tell you that much yet. Okay, here's the performance. So we train 10 times faster than Vanilla Bird and gain a 30% accuracy boost. So here, if this, let's explain this graph, right? We have the training steps on the x-axis and the validation accuracy on the y-axis, and you see, well, our blue line increases like way faster than the yellow line, and also converges to a higher accuracy. So how did we do that, right? This is just the result, but the interesting part is how is that achieved? So how that's achieved is we said, well, look at a typical document. Everybody is processing it like token by token, as if that is the only information there. But actually, our documents are structured such that we have sentences and paragraphs and sections. So in this way, we also structure the attention matrix. At the bottom part, I don't know, do I have a pointer here? Yeah. At the bottom, we have the regular tokens. So that is like this, the train is at the station, kind of like each word separately. And well, our attention summarizes that into sentence tokens, which are then in turn summarized into section tokens, which are then summarized into one document token, and this is the final like vector embedding that you get for each document. That is semantic in the sense that documents with the same meaning are mapped to the same point in the vector space. So yeah, we put this heuristic observation into an attention matrix over here. So I had just told you that, well, the entries in this attention matrix correspond to like how important the tokens are to each other. We basically say, okay, a lot of these computations are useless, so we blank them out, right? Like between the sentences, we don't care like how similar T3 is to T2, but we care about its relationship to all the other tokens in its own sentence. And then these inter-sentence similarities are going to be computed further up. So that's what we represent in this matrix here. Please ask any questions if you do have them as we go along. I'm happy to like take a break and talk a bit more about something that I didn't make so clear. But what that leads to basically when we set up attention matrices in this way is a diagonally block sparse attention setup, where very large parts of the attention computation are not actually needed to be done. You see here we only need to do these block computations on the main diagonal, but all this white stuff we don't need to compute. So that's saved compute, and that's why we are so much faster than BERT. But this, in order to like really have these savings, we need to have a like attention kernel, attention implementation that skips these blocks. So like modern things that do this are a flash attention, for example. If you just did this, let's say in NumPy, you wouldn't have time savings here. And that's why we went really into detail and did a CUDA implementation. So this is now, we are really at the bottom of the pit. This is the deepest we go, right? And thought about, okay, how do we sort our keys and values in HBM, in the high bandwidth memory, and load them into SRAM such that we can skip blocks that don't need to be computed, and we only like compute this main diagonal of blocks that I showed before. So this is the super in-depth part, right? As a result, of course, as in every research paper, like we made things better, so it's we're faster than flash attention on this use case. And you can also see that this like green line that I have here, this is the standard attention. We had to kind of stop computing it because that's quadratic in runtime regarding this input length, so we could like not even continue experiments there. So basically on this graph, yeah, maybe I should explain the graph. So we have the length of input, which is how many tokens go in, and the time per batch that it took. So how long it took us to compute, let's say, 16 of the documents. Yeah. And we are the lowest line here, which means we are fastest. Okay, so this long story is about how at Scholar Inbox we compute this item tower transformer. We don't do it completely dense. We have some sparsity that speeds up things and also improves our performance because of this heuristic. It's useful. Okay, that's that. Now to the cold start problem, which was the title of my talk. This is an observation about recommender systems, right? When we train a recommender, well, we need data to like the interaction data of the user. So we need to know what they liked and what they didn't like in order to make future recommendations. But when we don't have anything like that, then how can we start at a system, as a system? How do we even start? That's the cold start problem. And like prior solutions or proposed solutions to this include, let's say we just don't do recommendations, we just randomize our content and see what the user starts interacting with. But it's very infeasible because if you have like 1,000 papers come out, the user is immediately frustrated if they don't see like the thing that they really like. Then what's the worth of the platform? And of course our users start like deciding if they like us in the very beginning, and that's where we need to be good. Okay, and the other one which kind of works is, let's pick a category of interest. Let's say you like computer science, you like computer vision, and then we would be able to give you some related papers, but it's not very specific, and you need to have very good categories in order to do that. So it would, like for each research area, we would need to have a good category. This is a bit tricky. So we wanted a learned system, and also a learned system works really well. Yes, so now I'm going to explain how our active learning solution works. We can see recommendations here as a classification problem. So this user, this example user, has like 3 papers that they liked, that we know they liked, and 2 papers that we know they didn't like. And well, then we can train a classifier that separates these two groups very easily. Yes, so this is the problem in 2 dimensions. Of course, the problem really is like way higher dimension, but we project it into 2 dimensions. But a cold start looks like this, right? We don't know anything. So active learning is defined as an algorithm that interactively queries an oracle to label new data points with the goal of achieving high accuracy using a few labeled instances as possible. So we really want to be as fast as possible, getting to know our user, right? And in this, we iterate between user feedback and model training. The first step is we query a data point, any data point, because we don't know anything. So we ask them, how do you like this one paper? And after we do that, we retrain part of our model. But for efficiency, we freeze this very big transformer part, and we only train the super shallow user embedding part, which trains in 100 milliseconds. Unbelievable, right? But it's even on CPU. This is like really super shallow neural network. Yeah, and then we run inference and provide a list of samples that need to be labeled next. So which samples do we label next? Well, we have a look at the decision boundaries. So where is our classifier the least certain about which samples to provide to the user next? And well, that's at the decision boundary. So this thing in this point in red, that would be the next point that we query from the user. That's uncertainty sampling is one of the active learning strategies. Okay, and we do that, and after that we retrain, like with our very fast training. And of course the points move around and the decision boundary moves around because the points stay where they are, but the decision boundary moves around so that this picture that I take of the decision boundary now looks different. But we again have a setup where some points are close to it. So this is going to be the next sample. And this is a really sample efficient way to get to know your user in a recommender system. Yeah, so that's what our onboarding procedure looks like, right? You just get a paper you like or dislike, maybe you can skip, and you get fed more and more papers according to the heuristic I just pointed out. That's Tinder, huh? I don't know if you paid attention, but this procedure, you just swipe left and right. Well, that's Tinder. So we have like research Tinder basically, but instead of attractive people, we only have papers. Yes. Attractive papers, yes, the best. Okay, that concludes my talk. Please leave a rating. If you know anyone with a job, let me know. I'm finishing PhD now. Yeah, I'd like to take any questions if you have. Thank you. Oh, so many. Let's start from the back. You. Yeah.
One of the last slides, I saw that you were asking for 40 votes before you have finished the first training. Is this a fixed value, or is this adapted interactively during the first training process?
Yeah. I don't think 40 is the hard cap. It's like 30 or something like that. But this is not all required to be done in this active learning stage. So actually, we complement the strategies. So we start with like, you can name a category, so you're like roughly there, and then we like refine it. And once you select the category, we take like some representative papers of this category, and that also bootstraps your recommender. So if you want to reach like 40, but you bootstrap already with like 20 from the category, then you have 20 left or something like that. Yeah. Okay, yes. Yeah.
Maybe I misunderstood on this, but you showed like the dual architecture with like the query tower.
Mm-hmm.
But if the first stage only trains like the query vector at the end, where exactly does the tower come in? Like, what does it do?
So let's go back to this diagram. Yeah. Yes, this is correct.
Where does the query tower come in?
Okay, well, the user embedding is what comes out of the query tower, and we train the parameters of the query tower, which is basically one layer of MLP, so it's like super small. Yeah. Another question? Yes. Yeah. It is. Yeah, we got some good feedback. It's working. Yeah. Yes, please. Oh. Hmm. Yeah, so both speed and accuracy improved. So we could see this graph. Here we show that it improves over vanilla BERT in terms of accuracy by 30%, and also training speed, but also inference speed, of course, by 10%. And this is because of sparsity, right? Because like vanilla BERT does the full attention computation on its input. Everything that you give attends to everything else. No, not for this graph. Yeah, but you also see that it's faster, like for this. We're faster than flash attention on this graph. Yeah. Yes. Are you happy with that answer? You're okay with that answer, right? Okay, thanks.
I have a question. Probably that was already explained, but you made an embedding out of the many tokens, like a sentence embedding or something, or a vector at least of sorts.
That's right. Yeah.
How did you compute this sentence embedding? How did you use your tokens to make this
Mhm.
like a multi-layer perception?
Basically this. So we use a transformer encoder. We don't. You ask per sentence or like, because I mean, finally, what we need is an embedding for each document, right? In order to compare documents.
Approach, but I'm confused. How do you go from one hierarchy to another?
Okay, I see. So that detail is encoded in this matrix here. So if we look here at what tokens we outline, these are like the basic tokens, T3 to T6. And send is the, if you're familiar with, this is like a CLS token for the sentence. So this is like a summary token that summarizes this sentence. And this one token is connected to its adjacent sentence tokens and to its hierarchically above section token. So that is basically, I'm talking about this. Okay. I guess this left and right hand side, there is a little bit of discrepancy here, but like this sentence and that sentence, they're related. So they attend to each other. Yeah.
My question is how to obtain this representation of this sentence.
So how do we get this structure here for this attention matrix?
How do you get the values before the attention? Like how do you make a vector out of this? How do you turn your single tokens into a vector for your sentence?
Okay, so that is a question about tokenization, right? If you want to look it up, this is called byte pair encoding, which it's called byte pair encoding, BPE. This determines how the tokenization is done. So if you have a sentence, then we don't split it into like every word separately, but we do kind of syllable strategy, like each syllable has some meaning, right? And then after this byte pair encoding strategy is done, we obtain a vocabulary that tells us, you know, like which tokens are which, and they get an ID, and then they are embedded with a number vector, right? Like these number vectors you could, for example, initialize randomly or like more smartly. Yeah, that's how you get token vectors. Is that your question, or was that not quite your question?
Maybe. So you said that there's a strategy that already has like assigns an initial value for each of the vocabulary.
Yeah, you just fix that in the beginning.
Okay, so it's fixed at the beginning, and
Yeah.
then the attention takes charge of giving the values later.
Yeah, because like
Not really, but I get it.
yeah, so these token values then are processed throughout this transformer, and there are many weights inside of the transformer that will change how the values are, so that in the end you get a good embedding.
At the beginning, you just have all the vocabulary, which includes all the tokens, plus
Yeah.
all the sentences, plus all the sections, and then you make
Uh-huh.
vocabulary for this.
Yeah, you take all your training data and collect the frequencies of how often characters occur, and you determine the tokens that way. I don't know, I could explain byte pair encoding in detail if you want, but that's yeah.
In your vocabulary includes the sentences already? That's what you
No, in the vocabulary, the largest thing is basically a word that's in there.
and then they don't get an answer. How do you go from the tokens to the sentence embedding?
Well, that is this picture. So here are like 4 token embeddings. We just talked about how we get these, right? And then they are summarized into this sentence embedding via the attention computation, right? So we do the dot product between like this sentence token and all of the word tokens here, and sum it all up according to this weighted sum up operation, and that then becomes this sentence token. Of course, in the yeah.
Also a transformer process.
This is the heart of the transformer, the attention, right? Yeah. Of course, in the first run, this wouldn't make very much sense. It's just going to be like some combination, right? And then you have to do pre-training and do like a really long training process in order to get a transformer encoder to work. Yeah. Yes, please.
Is there a paper for this?
Yeah, this is a paper we published in Colm. And back there was a question?
So the input is that the focus is purely text, or you also have like to be able to
Yeah.
images. Like
Yeah.
I could imagine like formula and mathematical expressions could also be input.
Yeah, so that works, like we didn't do maths expressions apart from just like the text representation that they have. We tried figures, and that works like not even that great. It doesn't add that much, right? It's very hard to do figure understanding. That's another branch of like NLP research. Yeah, the biggest gains are from just text. And it turns out that like the way that people use recommender systems like this, they like just read the title and parts of the abstract and then can make a decision on what papers they like. So really there is not even that much gain from using full papers. It already works quite well with just title and abstract. Yeah. Yes. Yeah. Yeah. That's an excellent question. I really like this question. So what you see here, this attention matrix, is the result of multiplying the key matrix with the query matrix, with the value matrix. These two matrices are dense. But what we're interested in is a sparse result. And this question is one that was not solved by PyTorch when we did our project. To multiply two dense matrices and then only be interested in a sparse result was not solved. The other way around, yes, like if you multiply sparse matrices and want to get a result, then that was already addressed. But this way around was not, so we wrote our own CUDA kernel. A little bit later, then PyTorch also published an edition, and now you can just run this in PyTorch. You don't need our kernel anymore. Did you have a second question, or what? Yeah. Mm-hmm. Yeah. 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 So I mean, our paper was 2 years ago, and of course there has been more research since then. And yeah, if all you claim is a speed increase, then that's kind of dodgy, right? Like there must be also some accuracy, because we can leave out as many tokens as we want, then we're really fast. But yeah, there has been other progress as well. And there have also been like more famous approaches, such as like Longformer is a really famous approach, where they, instead of pooling in this heuristic way, they just pool like every 100th token or so, and then that also gives efficiency increases. Yeah. I think there was one question here in the chat. No, there was no question. That was just some instruction. Okay. If you're done, thank you very much.